Hello everyone, I'm Jungwon from Seoul National University. My research topic is efficient multi-agent trajectory planning with feasibility guarantee using relative Bernstein polynomial. Let me start my presentation. The contents are as follows. First, I will introduce my research motivation and I'm going to talk about proposed method. Finally, I will show you our experimental results. Recently, multi-agent systems are receiving much attention due to various applications such as drone show or cooperative transportation. For the successful operation of these systems, path planning algorithm is required to generate safe and dynamically feasible trajectories in a short time. However, it is challenging to satisfy all the requirements. There have been many researches about multi-agent path planning. One popular approach is a centralized optimization method. These centralized methods can generate optimal trajectories without deadlock, but they require hundreds of seconds to generate trajectories for view agents. Also, they have a risk to optimization failure due to infeasible collision constraints. Recently, many works have considered distributed methods due to scalability. However, they cannot guarantee the completeness at the obstacle-dense environments. To alleviate the drawbacks of two approaches, we propose a new efficient multi-agent trajectory planning algorithm. This method can generate safe trajectories without deadlock or optimization failure by utilizing relative Bernstein polynomial. And it can reduce the computation load by adopting sequential optimization method with dummy agents. Our goal is to generate continuous safe trajectories for n quadratures. We assume that each robot has different size and has the different dynamics limit. We also assume that prior knowledge of the free space is given in a 3D occupancy map. When we plan continuous trajectories in an obstacle-dense environment, it is difficult to handle collision constraints with a standard polynomial basis. In this region, we represent trajectories as an m-segment Bernstein polynomial. One of the useful properties of the Bernstein polynomial is a convexor property. Bernstein polynomial is always confined within the convexor of each control point, so we can use this property to formulate obstacle avoidance constraints. This property can be used to prevent intercollision between two agents. Since all agents have the same number of segments, relative trajectory between two agents is also Bernstein polynomial with this coefficient. Thus, we can use convexor property to formulate intercollision avoidance constraints as shown in figure 7. In this work, we formulate a multi-agent trajectory planning as an optimization problem. We designed the objective function to minimize the desired derivative of the trajectories. We consider waypoint continuity and dynamic constraints to generate continuous dynamically feasible trajectories. Collision avoidance constraints can be divided into two parts. For the obstacle avoidance constraints, we'll use safe ride corridor or SFC. And for the intercollision avoidance, we'll use relative safe ride corridor or RSFC. This is an overview of our algorithm. First, we plan discrete initial trajectories using a grid-based path planning algorithm. Next, we construct SFC and RSFC based on the initial trajectories. Finally, we optimize trajectories with SFC and RSFC constraints. We'll check the detail of each part in the following slides. As mentioned in the previous slide, many centralized methods have a risk to optimization failure due to invisible collision constraints. To overcome this, we utilize initial trajectories to construct collision constraints. Initial trajectories are defined as discrete paths that do not collide with obstacles or other agents, and we used ECBS algorithm to find them in a short time. After planning the initial trajectories, we construct safe ride corridor for obstacle avoidance. Safe ride corridor is defined as a convex set that models an obstacle-free space, and it must contain a part of initial trajectories to prevent optimization failure. To construct SFC, we first initialize small corridors to include the part of the initial trajectory, and we expand them until they meet obstacles as shown in figure 9. Similar to SFC, relative self-right corridor is defined as a convex set which represents a free space between two agents. RSFC also has to contain a part of relative initial trajectory to prevent optimization failure. The construction of RSFC is described in Figure 11. First, we convert the initial trajectory to the relative initial trajectory. Then, we perform coordinate transformation as shown in the right figure. Next, we linearize the collision constraint at the closest point to the origin. Finally, we can get RSFC by retransforming it to the original coordinate system. Return to our optimization problem, we can reformulate it as a quadratic programming form. Our objective function can be represented into quadratic cost, and convex constraints can be translated to affine equality and inequality constraints. Non-convex collision constraints can be converted to convex ones by using convexor property of Bernstein and the relative Bernstein polynomial. However, optimizing all control points at once can cause a scalability problem. Here, we propose the sequential optimization algorithm to reduce the computational load. First, we deploy dummy agents which move along the initial trajectories. Then, we divide the agents into several batches and plan the trajectories for one that avoid the dummy agents. Next, we update the control points of dummy agents with the result of current batch. After that, we plan the trajectories for the next batch sequentially. At the end of the iteration, we can generate collision and deadlock-free trajectories because all the agents are planned to avoid the previous batch. Furthermore, we can prove that there is no optimization failure for every iteration. This video shows the simulation results with 64 agents. Ellipses represent the collision models of quadrators, and gray boxes show the position of obstacles. As we can see in Figure 12, the minimum distance between quadrators is always greater than collision distance, which means that there is no intercollision between quadrators. To validate the performance of the proposed algorithm, we compare the results with previous work. In the previous work, we used a heuristic method to construct RSFC. So as described in the left graph, it does not guarantee optimization success when the agent size gets bigger. On the other hand, the proposed method shows a perfect success rate for all the cases. Also, as you can see in the right graph, the proposed method shows better performance in both objective cost and computation time when the number of the batches is larger than 2. Next, we compare the proposed method with one of the state-of-the-art SP-based method. As you can see in the second column of Table 2, the proposed method shows better performance in computation time. Furthermore, it requires less computation time than SP's single iteration. The third column shows the safety margin of each method, which means the ratio of the minimum distance to collision distance. In the case of SCP, the collision constraint is only applied to some waypoints of the trajectories. So, collision can occur at the section between waypoints. On the other hand, the proposed method always guarantees collision avoidance by utilizing the convexor property of relative Bernstein polynomial. Although the proposed method performs better in computation time and safety margin, it has a longer flight distance compared to SP-based method. We'll improve this part at the future work. The flight test was conducted with 6 crazy flight quadrators. All trajectories were pre-computed before the experiment. And we used Crazy Swarm framework to follow the desired trajectories. To summarize, first, the proposed method can generate collision deadlock-free trajectories in an obstacle-dense environment. Second, the proposed method guarantees the feasibility of constraint in the optimization problem. Third, the proposed method can compute safe trajectories for 64 agents in 6.36 seconds. Currently, we have released the source code on GitHub. If you are interested in our work, please feel free to visit our repository through this QR code URL. Thank you for listening to my presentation.